So we talked in 12.2 about how much energy is taken into or given off by different chemical reactions. And we figured that out by just using a set of tables. So you knew the values for all the substances involved, you could figure out the reaction. What we're going to look at in this packet is how we figure out how much heat is being given off by a reaction or given off by a process by how that heat gets transferred to another substance. And that's a process we call calorimetry. So calorimetry is used to measure the heat lost or gained by a substance to determine how much heat was produced by a reaction or process. So reactions are fairly straightforward. Process is something like a phase change, and we're going to look at how those work. To be able to do that, you need to know a little something about your heat. So the first thing we need to know is for calorimetry, Q, which is Q equals our heat, the Q lost by one substance has to equal the opposite of Q gained by something else. And we're going to look at how that works when we're getting into our math. To do that, we're going to use a formula that involves something called our specific heat capacity. The terminology is a little bit weird because you will see it several different ways. So you could see specific heat capacity, all of your words. You will sometimes see it referred to as specific heat. You will sometimes see it referred to as heat capacity. They all mean the same thing. All of them have to do with how much the temperature changes based on your mass and based on the amount of heat you put in. Because of that, your units are going to look a little funny on your specific heat capacity. It's always going to be joules per gram degree Celsius. All right, so the formula we're going to use for anything involving specific heat capacity is going to be Q equals M times C times delta T. We already said Q is our heat, and we measure heat in joules or sometimes kilojoules. Our M is our mass, and mass will be usually in grams. Our C is our specific heat. And that can be a capital C or a lowercase c, just like Q can be a capital Q or a lowercase q. It depends entirely on who's putting it together. Our delta T is going to equal our change in temperature. And because it's a change, that can be left in degrees Celsius. We don't have to worry about Kelvin. All right, so let's look at how this works out in the math. So flip in your packet to the Notes and Guided Practice page. These first two, you're going to do along with me. So this is a good calorimetry example. The heat released from burning alcohol is used to heat 100 grams of water from 24 to 39 degrees Celsius. We want to know how much heat was released from the burning alcohol. And we know that the heat from the alcohol is what's heating our water, so we can just do a simple Q equals M times C times delta T. Because Q, our heat, is what we're looking for. Our mass, it tells us, is 100 grams. Our C is going to be our heat capacity for our water, and you're going to be given this in a table someplace. You need to be aware that our heat capacity for water, if it's liquid, is always 4.184 joules per gram degrees Celsius. We're going to talk here in a minute about what happens if it's not liquid. All right, and then our delta T, remember it's a change in temperature, so it's our final temperature, which is 39 degrees Celsius, minus our initial temperature, which is 24 degrees Celsius. And that's going to be 15 degrees Celsius. So we're just going to plug those things into our equation. So Q, which is what we're looking for, equals our mass times our C times our change in temperature, which is 15 degrees Celsius. And I already said, I know your units look a little funny on your specific heat because it's joules per gram degrees Celsius, but if you look at it, my grams and my grams will cancel out. My degrees Celsius and my degrees Celsius will cancel out. That leaves me with joules, and since I'm looking for heat, that's what I know I'm going to want. So now I just multiply my numbers together. So we have 100 times 4.184 times 15. And so the amount of heat that's released from my alcohol absorbed by my water is going to be 6,276 joules. All right. A blacksmith lowers 3.2 kilograms of an unknown metal at 130 degrees Celsius into 22 liters of water. And the specific heat for water, when we're dealing in kilograms, is going to be 4,186 joules per kilogram per Kelvin. The initial temperature of the water was 43.5 degrees Celsius, and the final temperature of the water is 45 degrees Celsius. What is the specific heat of the unknown metal? So we're given a lot more information here, so it gets a little more complicated, but it's going to work out to be the same basic algebra. All right, so things we know. We know a lot more, but the first thing we need to remember is that Q lost by one thing has to equal the opposite of the Q gained by something else. So you can take MC delta T for one substance and set it equal to MC delta T for another substance. So we're going to write down all the things we know. We know that the mass of our metal is 3.2 kilograms. We are looking for, because that's what our problem says, the specific heat of our metal. The change in temperature of our metal, remember, is going to be our final temperature minus our initial temperature. If we look back at our problem, our initial temperature of our metal, it tells us we have 130 degrees Celsius. It doesn't specifically say our final temperature of our metal, but something we need to know, we talked about in 12.1, that things are going to try and reach thermal equilibrium. So they're going to try to be the same temperature. So when everything's finished changing temperature, the water and the metal are the same, which means our 45 degrees Celsius is going to be final temperature for both. All right, so that's our metal. Now we want to look at our water. The mass of our water isn't given, we're given a volume, but just like grams and milliliters, kilograms and liters work out to be the same. So if we've got 22 liters of water, we have 22 kilograms of water. It gives us our C in the problem, which is 4,186 joules per kilogram per degree Celsius. Kelvin and Celsius are the same size. You can use them interchangeably at this stage. And then our change in temperature, we're going to do final minus initial. Our final temperature was 45 degrees Celsius. And then minus our initial temperature was 43.5 degrees Celsius. All right, so let's do our change in temperatures first. So we have 45 minus 130, which is negative 85 is our change in temperature for our metal. And then we have 45 minus 43.5, so I could say 1.5 degree temperature change for our water. So we're going to plug this all into our equation. So our mass of our metal is 3.2 kilograms. Our C is what we're looking for. Our change in temperature is negative 85 degrees Celsius. And that equals to our mass of our water times our specific heat for our water times our change in temperature for our water. So now we want to get everything reorganized. We're trying to get C by itself. We want to know the specific heat of our metal. So to do that, we have two options. We can either multiply our numbers and then move things, or move things and then multiply. I personally like to move things first in this case. So we're going to divide on this side because we're trying to get C alone. We've got to divide out our 3.2 kilograms, and we've got to divide out our negative 85 degrees Celsius. We're going to do the same thing on the other side. So that's 3.2 kilograms, negative 85 degrees Celsius. This is why you've got to pay attention when we're putting things in. You want to make sure the bottom part's in parentheses, because if it's not in parentheses, then you get a ridiculously large number. All right. So this gets us, at the moment, C equals negative 507.86, but you can't have a negative specific heat. That's going to be positive. There are a couple ways we can fix that. Like I said, the heat loss equals the negative of the heat gain, so you can either just put a negative in front of this whole side, or you have to remember that one side you have to do final minus initial, one side you have to do initial minus final. Either way is fine, or if you just end up with a negative C, just make it positive. All right. All right, so hopefully you tried this guided practice problem on your own. I know this one's a little bit more complicated than most of what we've been doing, but it shouldn't be too bad. So what we're doing here, we have the specific heat problem. We have if 20 grams of silver at 350 degrees Celsius are mixed with 200 grams of water at 30 degrees Celsius. We want to find the final temperature of the system. Now what we need to remember for this one is that delta T equals TF, our final temperature, minus our initial temperature. So that's what it means for a change. So let's keep that in mind as we're figuring out what information we know. So we know we have two sets of information. We have our metal, which is our silver, and then we have our water. So things we know about our silver: we have a mass of 20 grams. We have our specific heat, which is 0.233 joules per gram degrees Celsius. And we don't have our change in temperature. We do know our initial temperature, which in this case is 350 degrees Celsius. For our water, we know we've got 200 grams of water. We know our specific heat for water is 4.18 joules per gram degree Celsius, because you've got that in your table down here. And we know our initial temperature for our water is going to be 30 degrees Celsius. All right, so now let's plug in everything we know. And remember that we're looking for TF, but TF will be the same on both sides. So for our metal, we've got our 20 grams times our 0.233 joules per gram degree Celsius. And we've got times our change in temperature. Our change in temperature is going to be our TF, which we don't know, minus our TI, which is 350 degrees Celsius. Then we're going to do the same for our water. So then we're going to have 200 grams of water times our specific heat of water times our change in temperature. And to make sure our signs work out okay, because remember it's heat equals the opposite of the heat, we're actually going to do this as initial minus final. So we're going to go ahead and put our 30 degrees Celsius in minus our final temperature. That'll fix our sign issue. All right, now we're going to want to do a little more complicated math. It's not too bad. You just have to remember the distributive property. So when you're doing algebra, anything outside the parentheses is multiplied by both things inside. So we're going to end up with 20 times 0.233, which is 4.66 times our TF, minus our 20 times 0.233 times our 350, so that's minus 1631, equals our 200 times our 4.18 times our 30, because we're going to multiply all of these together, and that's 25080 minus our 200 times our 4.18, and that's 836 TF. All right, now we want to get TF by itself, which means we want to get all our TFs on one side and all our things that don't have TF on the other. So if we're currently subtracting, we're going to add 1631 to both sides to get rid of it. Okay, and we can also add our 836 TF to both sides to get rid of it. All right, so then those go away and those go away, which means we get 4.66 plus 836. So we have 840.66 TF equals 25080 plus 1631. That's going to be 26711. And to get TF by itself, because we've got 840 times TF, we're going to divide on both sides. All right, and so then we actually do that math. And that's going to give us a final temperature of 31.77 degrees Celsius, which makes sense because we've got a fair bit more water, and water's got a much higher heat capacity, so our water temperature shouldn't go up very much, even though our silver temperature is going down a lot.